All right, so maybe I'll introduce myself first. So I am Aurélien Bellet. I'm one of the co-organizers of this Federated Learning One World seminar. So this is with Peter Richterick, Virginia Smith, and Dan Alistar. So I'm going to be hosting today's talk with the help of Samuel Horvath, who handles actually most of the logistics. So thanks again, Samuel. The goal of the seminar for people who haven't joined before is to provide essentially a forum to discuss the latest scientific results in all aspects of federated learning. So we hope to cover distributed optimization, learning algorithms, privacy, security, crypto, personalization, communication compression, systems, hardware, applications, and so on. So far, some of these topics have been a bit more represented than others. So we are planning some talks to try to be quite broad in the coverage. So the speaker today is Peter Kairouz. Thanks a lot for accepting the invite. So Peter is a research scientist at Google. He received a PhD in electrical and computer engineering from the University of Illinois at Urbana-Champaign in 2016, and he was also then a postdoc at Stanford. He's working on the mathematical foundations of privacy, in particular differential privacy, and on the design of privacy-preserving algorithms for distributed data analytics, information dissemination, and federated machine learning. And today, I think Peter will talk about federated analytics, so where one has distributed data sets and privacy constraints, as in federated learning, but the focus is not so much on machine learning, but rather to extract information relevant to sort of more generally data science tasks. So before giving the floor to Peter, I'll just quickly explain how the audience can ask questions. So we'll do that during the talk. All mics are off by default, but you can use the raise hand features in the participants menu, or you can also write your question in the chat, and then Samuel or I can ask the question for you, or we can turn on your mic so that you can ask the question yourself. Okay, so I think I've said everything, and Peter, the floor is yours.
Yeah, thanks, Aurélien. And hi, everyone. I'm really excited to be with you to talk mostly about federated analytics, but I figured that before we jump into federated analytics, might as well review federated learning for those who are just starting to get into the field. So, you know, we're all here because we like federated learning. That's the title of this seminar, and might as well just go a little bit over a definition of what we mean by federated learning and what are the unique characteristics of federated learning. So the way we view federated learning, and this is a definition that appeared 6-7 months ago in a paper that we put up on arXiv with many academics and many researchers at Google. We view federated learning as a machine learning setting where multiple entities, they collaborate jointly in order to solve a learning problem. And they do it under the coordination of a central service provider. Now, the most important part here is that their data is never transmitted to that central service provider. Instead, they send focused updates that are ephemeral. So you compute something on your data. Instead of shipping the data to the server, you only ship the answer to the computation that you've done on your data. And hopefully that computation removes a lot of the personal sensitive information and gives a very brief summary of the answer that is needed in order to compute that learning task. So let's dig a little deeper. There are two main settings of federated learning. One of the main settings that we focused on at Google is called cross-device federated learning. This is a setting where training happens with a server, which is a company offering services, and then the clients are phones or tablets. And so you have here many such clients. By many, perhaps you have millions, hundreds of millions, even up to a few billion devices. So think of these devices as sensors, tablets, or phones. That's the scale of this problem. And each device has very little data because, again, we're talking about phones, So do not expect to see these very large, massive data sets on people's devices or phones. So the scale of the problem is that you have way more devices than you have data per device. And they want to collaborate in order to train a prediction model or a recommendation model of some sorts. And then finally, once the model is learned and it's vetted by an engineer at the company, it could be deployed to be used on device. Now, this setting of cross-device federated learning, it operates in the following way. The initial model, you can start from a randomly initialized model or a pre-trained model on some publicly available data set, is sent to a device. On that device, you can see that the local data store, which contains training examples, is used in a certain computational framework. We use TensorFlow, you might use other computational frameworks to update the model. And I'll tell you in a bit what we can do in terms of updating the model, because there are many different recipes we can follow to update that copy of the model. And once we get this updated model, it's sent back to the server. As you can see on the slide, the server gets many updates from devices that are participating in this round. It aggregates them somehow. We can talk about different aggregation primitives and rules as well on the server. And then we get a new model here. This is the green one on the server. And we can go back and forth in many rounds. So let's talk about the different algorithms and then some numbers in terms of scale of how many devices do we have per round and how many rounds we have to do. In terms of algorithms, one of the most basic algorithms that work quite well in practice is called the federated averaging algorithm. And this federated averaging algorithm, which I assume some or most of you are familiar with, operates as follows. On the device, when you get a copy of the initial model, what you are going to do is you're going to run some number of stochastic gradient descent steps on the data points that you have. So that's very easy. You just do SGD for a number of steps. Once you update that model and you send it back to the server receives many updates from many devices. It simply just computes the weighted average. So it's weighted by the number of training examples that were used on each device. It's as simple as that, very easy. You're just doing some number of SGD steps on the device, and then on the server, you're doing some weighted average. And this is called federated averaging algorithm. Now, this is not necessarily the best, especially in scenarios where these devices have data coming from different distributions. So you may want to do something different, both on the server and on the client. And we'll talk about it in a bit. But in terms of orders and numbers, what we usually do in production, this is just to give you a sense of how we operate. We usually have about anywhere between 100 to 1,000 users per round. That's how much clients you can support in a round. Keep in mind there are some limitations in terms of bandwidth of the server, in terms of talking to people, in terms of device availability. Not all the phones can be online all the time. They have to be connected to Wi-Fi. They have to be plugged into the wall, charging, because we don't want to deplete people's batteries, so on and so forth. So there are many criteria that have to be satisfied in order for devices to be eligible to participate. And usually, in order to get a good quality model, we have to do many rounds. We do anywhere between 100 to multiple thousands of rounds to get convergence. And each round takes anywhere between a minute to 10 minutes. So just to give you a perspective, this is not a process that takes a few hours in order to train a model. This is a process that takes more than just a few days, sometimes a few weeks, in order to get the high quality model that we want. Keep in mind that there are some hyperparameters that we usually tune when we're doing optimization, like learning rates, different styles of optimizers, so on and so forth. And so if you want to try out a bunch of hyperparameters, then it could take more than a week in order to train a high quality model. By the way, please feel free to ask questions and stop me whenever I say anything that is not clear for you, or if you just want to share comments. Now, I told you there are two settings. What I just touched on is the cross-device setting. The other very popular setting is the cross-silo setting. In this setting, you still have a server and you still have clients. It's just the scale is very different. Here, instead of the clients being phones, and tablets or sensors. It's institutions. Think about them as banks, think about them as hospitals, or even schools. So now you have far fewer clients. Now you can have 10, maybe 100, up to 1,000 clients, but we're not talking about millions and hundreds of millions or billions of clients. It's a very different scale. And these institutions now have a lot of data. They can have massive data sets. Think about a network of hospitals. Each hospital can have thousands or maybe even tens of thousands of patients. And so you have records about each and every single individual patient. So now we are in a regime where we have far fewer clients than we have data per client. So it's a very different dynamic. And that's why these two settings, even though they are both federated learning, they have very different characteristics. In fact, cross-device and cross-silo federated learning do share some common characteristics with an even broader area of machine learning, which is called distributed machine learning. And oftentimes people tell me that both areas are essentially the same, but they are not. They share commonalities, but they are not exactly the same. So let's try to take a look at how they could be the same and how they're not the same. And this is one table that's showing some of the common characteristics and some of the differing characteristics. To me, one of the most kind of important differences between federated learning, both the cross-silo and the cross-device settings, and the distributed machine learning setting, is that in distributed ML, you do have the luxury to take one big massive data set, shuffle it all together, join all the records, and shuffle them, mix them, and then partition it into jobs that are sent to different workers in the data center. This is really important because once we do that, what we are doing is each worker is seeing a balanced data set. So they are all going to see more or less the same data set. And the statistics of the records of those data sets that are sent to workers is essentially going to be the same from one worker to the other. Whereas in federated learning, both the cross-silo and the cross-device, we don't have the luxury of combining all the data in one place, shuffling the data, and then redistributing it to workers. So what we end up with is something where you have very imbalanced loads. Some clients can have thousands of training examples. Others can have only tens of training examples or even no training examples. Some people have some preferences in terms of how they type on their keyboard and what they like and what books they read, so on and so forth. And others have very different preferences. So there's a lot of non-IID-ness in the problem that we have to deal with. And privacy essentially implies that we cannot combine the data, shuffle it, and redistribute the computation. Now, there are other also differences. Just by looking at things like distribution scale. For instance, in the data center, we expect to have anywhere between tens to hundreds of workers, maybe up to 1,000 workers running parallel jobs, whereas in cross-device, we just talked about the possibility of having up to 1 billion of such clients. So these are all interesting differences. There are other differences in terms of computational bottlenecks. Workers in the data center tend to have really good computational power. So we can run very complex computations without having to worry about, will these computations finish in time? Whereas when we compute on devices, say in the cross-device FL setting, our phones have very limited computational power to run these massive machine learning computations. Our phones are also unreliable. They drop out, they lose connection. Bandwidth in terms of communicating these models and updates back and forth between server and phones can be an issue. So we need to make sure we are compressing these updates or we're respecting some bandwidth restrictions. And all these things make federated learning, especially cross-device federated learning, somewhat far away from distributed ML. There's an even other setting that people also often confuse with federated learning, which is this fully decentralized learning setting, where you have a graph of nodes or clients, and they also are trying to collaborate in order to train a common model on their data. And this is a very popular and a very important setting of machine learning. It's also interesting for latency, it's interesting for privacy. but it's not FL because there's no presence of a central service provider. This federation of devices under a service provider is absent and fully decentralized. So this orchestration is very different. In fully decentralized learning, usually there's a peer-to-peer topology where a node or a client can talk to some of its neighbors, but it cannot talk to others. And so there are many interesting characteristics and also some of the restrictions that fully decentralized learning usually studies that makes it somewhat different from federated learning. All right, I think this is a good point to stop and see if there's any question from anyone. I believe there's none.
Yeah.
We have one
question from Ahmed.
Yeah.
Hello, Peter. Can you hear me?
Yes.
Okay, so I wanted to ask if we could go back to the previous slide, like the one with cross-device and cross-CLO. When we represent federated learning, we have first a finite sum problem that tells you that each client has its own loss function, and then each of these functions can itself be represented as a finite sum problem, right? In cross-device, as far as I understand, because the number of clients can be so large and they can be available only stochastically, so we do not assume that the clients constitute a finite sum, but that they come from an expectation. Like, what do you think? How do you think the difference between these two translates into assumptions when we're trying to think about optimization?
Yeah, that's a very good question. So there is a nascent effort that tries to do some modeling of, if I'm trying to do optimization, how should I go about thinking of optimization in the cross-device FL setting? And there are now a few papers that attempt to design a very mathematical framework for this setting. One approach, there's no consensus, by the way, but one approach would be to say there is a distribution over client devices. And what you do is you pick from this distribution a client index.
Yeah.
Once you pick a client index from this distribution, you now have a distribution over the data, over X and Y. Those are your the features and the labels that you're going to use to do machine learning. And so now what you're doing is you've reduced your problem to doing optimization over one single distribution. But obviously the way the loss is framed is you have two expectations. The first expectation is over the distribution of clients, where you have to pick a client index from. And then the other expectation is the classical expectation that you see in machine learning, where you're doing an expectation over the data distribution, both the records and their labels. So that's one way to go about it. And then in order to get some convergence guarantees, you have to make assumptions in addition to the classical assumptions that people make, convexity, Lipschitz gradients. You can assume something about the space of clients. So you can assume that those clients do not have distributions that vary too widely. So you can impose some distance constraints across the distributions of the client.
Yeah. So final thing, the number of clients here is variable, right? So it changes. So is there some sort of, let's say, new client method, or like how do you handle new clients?
It's a very good question. So it's not exactly the topic of my talk, but the idea here, there are two things. One is when you do federated learning, you're training on a fleet of devices. And as you mentioned, the fleet of devices can change with time. New devices can come in, can appear at any point in time. People buying new phones, or just like people becoming eligible by upgrading their operating system or downloading the federated app or something, whatever app we're talking about. So that's why in addition to training with federated learning, there is a step where you do personalization. That's important. So after you're done and you train your model, you get a global model that we're satisfied with, that works well on the fleet of devices that we've seen during training. We did A/B testing, and we've deployed the model. If you just deploy the model and that's it, then you do not expect it to always work well, especially for new clients that appear after deployment, or after training. So what we need to do is we need to do some personalization. We need to take that deployed model and also do some local training in order to personalize it to devices that we've deployed it to. And that's an important step. But personalization is a very big area, and it's not really the focus of this talk. All right, should we keep going?
Yeah.
Thank you so much.
Yeah, thanks, Matt. All right, so there are many open problems, and in fact, the questions we got from Ahmed do allude to these open problems. For instance, on improving efficiency and effectiveness of FL, one of these questions in the top left corner of this slide is, how do we personalize? Because we're going to see new devices. How do we make the whole training process more efficient? By reducing the wall clock training time, using compression techniques, using more efficient optimization algorithms, adaptive optimizers. I think Zach Charles from Google a few weeks ago in the seminar spoke about strategies for optimization, both on the server and the client. So there's a lot of very interesting open questions. How do we do things like reinforcement learning? How do we do unsupervised machine learning? How do we branch out to new areas of machine learning with this federated concept? How do we do debugging? Debugging is a big question because we now do not have access to the data. So if the model is failing, we don't know what's leading to this failure. And there are many other questions here on improving efficiency and effectiveness, lots of interesting open areas. On the privacy front, there's also a big question. What I described is very nice because we're not shipping the data to the server. So already there's a big win on the privacy front. We're only sending those minimized focused updates that we mentioned, but we don't get any rigorous guarantees by saying ship minimized focused updates. If you go talk to a differential privacy expert or a security expert, privacy researcher, they would tell you, well, I cannot quantify rigorously any gain. So we need to have a very nuanced story for privacy. This is called privacy in depth. And in order to address that, we need to know what private information might each actor in the system have access to. So there are many players. There's the client, there's the server, there's somebody who's observing the network, there's the devices that I eventually deploy the model to, there's the engineer at the company who is doing the A/B testing over the model. All these players are seeing different pieces of information. And in order to address this privacy question rigorously, we need to look at what does each player see. And so, of course, we talked about minimized data exposure, focused data collection, anonymous, ephemeral. These can be end-to-end encrypted. For the engineer, we only show them the aggregate model, so they are not seeing those intermediate updates to some extent. So all these principles do provide gains on the privacy front, but if we want to be 100% rigorous, we need to use tools from cryptography, and we need to use tools from theoretical computer science. We need to use modern encryption, we need to use SMPC, multi-party computation, local differential privacy or central differential privacy. Those are things I'm going to touch on in this talk. Maybe some auditing techniques, secret share, membership inference, if those are things that you may have worked on. They're not really the focus of this talk. I'll give you a pointer to where you can read more about all of them in a bit. But we need to use these complementary technologies in order to be able to give rigorous guarantees against different threat models, depending on what actor is malicious or what actor is compromised. So there's a lot of research to be done on this front as well. Robustness to attacks and failures. Bugs can happen, devices can drop out, devices can be hacked. Some of the data we're training on can be poisoned, as you can see in the slide, those red local data stores or models. So how do we provide defenses against those attacks? There's a very interesting area of research that's growing under federated learning that looks at robustness to these attacks. people trying to poison the data or trying to poison the models and trying to mess with the model in many different ways. And as you can imagine, federated learning, because we are shipping updates to devices, we're essentially creating a surface of attack here. And so it's important to make sure that that surface of attack is handled properly through algorithms that could give defenses against any potential attacks. Other areas include fairness and addressing sources of bias. For instance, in cross-device federated learning, as we saw before, you can have different statistics and different preferences for different users and clients. My preferences, the way I type, the way I use my keyboard, or the YouTube app, videos, books I watch, places I go to, are possibly very different from each one of you. And so we cannot expect a model to work well for everybody all the time. And so how do we make sure that we are being fair to minority groups in the training set? How do we make sure that when we're sampling clients per round, and we're doing all these rounds, we are having a representative sample of the global population? We're not missing on some minorities. For instance, people in some countries have poor internet connectivity or older phones. Are we making sure that we are representing those people? Because this is a very complex training infrastructure, and sometimes it might imply that we cannot take everybody. And so there are lots of very interesting open questions, and I invite you to take a look at this beautiful paper that we put up together, again, a few months ago, 6-7 months ago. It's called Advances in Open Problems in Federated Learning. It has 58 authors from 25 institutions. It really is a very comprehensive summary of all those things I touched on very quickly and very briefly. And you can learn more about them in depth. Aurélien is actually on the paper, the co-host today. All right, but today I want to focus much of the time on analytics, which you know, I'm referring to it as federated beyond learning. And so in a new blog post from about a month or two ago, we talked about federated analytics. And federated analytics is in many ways similar to federated learning, so do not expect to see something remarkably different, but it is also different in many ways, and that's what I would like to touch on. So what is federated analytics? It's the practice of applying data science methods to the analysis of raw data that's stored on people's devices. So it's the same essential setting. You have cross-device, you have cross-silo federated analytics, different paradigms. You have data on people's devices. It could be, you know, data with labels or without labels, location traces, views of videos or searches or whatever it is, clicks and swipes, so on and so forth. And we would like to do some analyses on the data. We don't necessarily want to train a classification model or a generative model on people's data using optimization frameworks. Rather, we want to just get insights. We want to do data science type methods, and I'll talk about it in a bit. And so it's essentially the same set of characteristics, the same set of issues, the same set of benefits on the privacy, on the latency front, so on and so forth. So what are the kinds of questions we are looking at under federated analytics? And by the way, many of the questions that I'm showing on this slide are actually open problems. We don't have an optimal solution in some sense to many of the questions that I'm putting on this slide. So when you think about federated analytics, you should start thinking about statistics and then open up the realm of possibilities. Some of the statistical quantities that we care a lot about, and many different service providers care about, are things like quantile estimation. We want to learn these percentiles and quantiles. We want to count events, distinct, unique events or elements on people's devices. We want to compute histograms over closed sets, or we want to discover those heavy hitter elements and open sets. We want to do density estimation or heat maps. We want to do selection of some random data subsets. You know, you can even open up the space to go beyond statistics and think about SQL operations. This really suddenly becomes a widely open question about how we design federated analytics. But you can see that these sets of questions are somewhat different from core optimization questions where we are trying to train a neural network or some algorithm for classification or generation. So hopefully, the distinction is a bit clear, even though there is a significant overlap between federated learning and federated analytics. And in fact, there's plenty that I can talk about here. All these questions are very interesting and of high impact. I invite you to think about them if you have time or if you are doing research on this front. But the one question that I'll talk about for the rest of this talk is the heavy hitters problem. And heavy hitters and histogram are closely related. So you're going to see that in the process of solving the heavy hitters problem, which I will define in a bit, I will be doing histogram estimation. So let's see what the heavy hitters problem is about.
Yeah, sorry, before you go ahead with the heavy hitters, I wanted to be a bit maybe annoying and ask you, in your opinion, what are the main differences between these federated analytics and maybe the work that exists in distributed analytics or IoT kind of analytics, where I think probably there is quite some work in maybe other communities of people that have looked at similar problems where also the data might not be IID, unlike this distinction that you were making also with distributed machine learning. So what's your take on that? Do you think maybe some of these problems have been solved to some extent in other communities? Or
that's a fantastic question. I think there are many, first of all, I don't like to think of federated analytics as different from things that we've seen in the past. It is perhaps a new name that captures a slightly broader set of problems or regimes, but it can very much encapsulate a lot of the things, for instance, IoT analytics over sensor networks or others. Now, having said that, even telemetry type applications, for instance, some of the audience may be familiar with Rapport, which is a technology from Google from 2014 that can very much fall under the umbrella of federated analytics, because even in that technology, for those who know the technology, we do minimized focused updates, and we'll talk about them. And we do it in a privacy preserving fashion. We don't ship all the data, and we expect to have non-IID data across users. And so I'm not trying to sell federated analytics as this is for the first time something that nobody has ever thought about. It is something that builds on a long line of research in the community, and it very much encapsulates many of the things that people have looked at. So I agree with your observation, Aurélien. One thing, though, that I would like to point out here is that the setting we are mostly focused on, if we look at cross-device federated analytics, has some systems challenges in terms of we need to run in rounds because we cannot talk to 100 million clients at once or a billion clients at once. They're not available for starters, right? Some of them are offline, they drop out, there's spotty connection, they're not connected to Wi-Fi or unmetered network or plugged to the wall. And so there is, in many ways, a real benefit to doing this iteratively, because now we can do interactive algorithms. So we can keep a server state, and based on that state, we can have clients in different rounds do different things. And that's what I'm going to talk about in this talk. Interactivity becomes quite interesting and perhaps quite powerful, something which theoretically we have not resolved yet. And we can do lots of interesting things, but I would like you to keep in mind those defining characteristics of the cross-device setting that could possibly give a new spin on some of the problems that have been explored in the past in other contexts.
Right, thanks, which is what you do, I think, in this heavy hitters problem.
Correct. Yeah, so they are. We'll see it in a bit. So let me define the heavy hitters problem. Some of you may have seen heavy hitters in the past. Some of you are seeing it for the first time. So this is a problem where each device has a set of words. Think about it as, this is your phone, and you type on your phone. You use your keyboard all day, every day to write emails and to chat with family and friends and to look things up and search and do so many things on social networking apps. And so the keyboard is such an app that is underestimated because it has a lot of AI that's happening under the hood. There's a lot of analytics in terms of doing spell checking, grammar correction, auto completion of the word, next word prediction. Some of the newer keyboards can even like make suggestions about copy pasting stuff. They can even like give you suggestions for what to look for or where to go, so on and so forth. So the keyboard is getting smarter and smarter. So there's a lot of analytics and a lot of AI and machine learning that are happening under the hood. And so one of the basic questions that we may be interested in is if people are typing words on their keyboards, and I would like to track new popular words. For instance, nowadays, everybody is talking about COVID-19 and wildfires and lots of different events that are happening. There's the elections. And so there are new terms that are popping up, new abbreviations. And one very important question for service providers, the people who are developing the keyboard at Google or in other companies, they may want to know what are the trending words, or what are the new popular things or topics that people are talking about. And so in some sense, what you would like to do is you would like to figure out these words that are frequently typed on many, many clients. But in many ways, you don't want to learn the words that are infrequent, because those infrequent words, if there's a word that only one client types, then you're breaching their privacy. It could be their social security number, it could be their credit card number, it could be some very personal issue that they are discussing with a parent or a friend or a colleague, so on and so forth. So how do we do heavy hitters discovery, those popular, heavy, frequent items in a federated fashion while respecting the privacy of the users? Now, for the rest of the talk, I'm going to focus on a very simple setting where each device has one single word. This is without loss of generality. I can tell you very briefly at the end how we can extend it to many words per device. So I don't want you to think of this as limitation at all. It's just for simplicity of exposure. And we're going to also assume that we only want to discover words, but everything I will talk about can apply for other domains of data. It doesn't have to be words or English words. It can be anything. It can be URLs. It can be location. It can be clicks or things you've looked up. So I don't want you to think that there's a restriction to words. This is very general, but just to ground the problem in an application and to make the exposition easy, I'm going to focus on words. All right, so I talked about privacy, that privacy is paramount, and so that's why we're going to use this notion of differential privacy, which I hope some of you have seen it, but if you have not, I don't want you to be worried because I'm going to go over it very quickly. So what is differential privacy? Differential privacy is the science of learning about aggregate populations, so computing averages or means or sort of arbitrary queries on aggregate populations containing many clients and many users without learning specifically anything unique about one individual user or one individual client. And so traditionally what we do is we have a data set that contains many people records, and we apply a query on this data set. For the sake of this talk, you can assume that query is grab all those frequent words from the data set, right? M of D here can be either, give me all the frequent words, frequently typed words across users in this data set, or you can think of it as build this classification model for me. So this is how we usually do it. We have the query computation, which could be doing optimization, or it could be computing sums, or taking a max, a mean, a mode, whatever, under the hood, under this query box, you can do a lot of fancy calculations and computations on a data set. Now, if you do this in a deterministic fashion, so if every time I query the data set, I get a deterministic answer, then it is easy to see that this is not privacy preserving. And the reason why it's not privacy preserving is because if there's an adversary, an attacker, that somehow colludes with everybody in the data set, except for one person, say I'm after Aurelian's data, I want to find something about his records, or I want to know if he is in the data set or not, So all sorts of questions that an attacker can be interested in. I can go and collude with everybody else and grab their values and data points, and then take the result of the query and subtract out everybody's values from it. And then I can suddenly discover Aurelian's value, which is problematic from a privacy perspective. So the first step in differential privacy is to randomize the output of the query. So that's why when you compute the query, there's a randomization step, perhaps internally to the query itself, or just some noise addition. So that now every time I compute the query, instead of getting a deterministic fixed answer, I now would get some random answer. And so you can see on this plot that I'm showing you on the slide, there is a distribution over the query results, over the output of this query. And this is very important, because now if I collude with everybody and I get their values and I subtract out the values from the query result, I'm not going to get Aurelian's result. I'm going to get Aurelian's result plus some noise. So there's going to be some uncertainty in what I will get. And that uncertainty is going to provide rigorous privacy guarantees. So just to be a bit more specific, the way we should think about it here as we should take two data sets that are exactly the same except for one user. So in this case, I have Alice, Bob, and Carol in D. And in addition to Alice, Bob, and Carol, I have Dan, a fourth user in data set D prime. And if I run the same query with the same randomization on both data sets, D and D prime, I would get two answers, the answer on D and the answer on D prime. And these two should have different distributions. If they have exactly the same distribution, if taking out Dan or putting Dan in the data set does not lead to any change in the statistics of the output of the query result, then I can easily figure out whether or not Dan is in the data set or their data. So what differential privacy says is that these two distributions, with or without Dan, they have to be essentially close to each other. Because if they're very close to each other, then it's hard to distinguish whether or not Dan participated. And so the way we measure closeness in differential privacy is not important for this talk. There are two parameters, epsilon and delta. And ideally what we want is we want both epsilon and delta to be small. That's how you should think about it. Roughly, we want epsilon to be a single digit. 1 is usually a good choice of epsilon. There's a big question of how can we choose epsilon. That's very separate topic, orthogonal to this talk. And delta, usually we choose it to be something on the order of, something inversely proportional to the size of the data set. So 1 divided by the number of records in the data set. Now, this may not seem very obvious to many of you, especially those who have not been working on differential privacy, and that's okay. But if you've seen differential privacy, this will be rather, just a restatement of everything you've known for a long period of time. But what is perhaps new to many is how we use it in federated averaging. Remember, we talked about federated averaging before, like 20 minutes ago. The way we introduce differential privacy into this framework of federated averaging is as follows. It's actually quite easy. When a client updates the model, this is what I'm showing inside this device, this tablet on the left-hand side. What we're going to do is we take that model update, which you can view it as a vector or a tensor, and you clip its L2 norm. You bound its sensitivity. You do like an L2 norm projection. This is important because we want to essentially limit the contribution of the user. We don't want users to send us arbitrarily large updates. We want to make sure that we cap how much the user can make a contribution. And that's intuitively very important for privacy. And then when we get all the clipped updates from users and around, you can see now on the server, there's these clipped updates. We aggregate those clipped updates, and then we explicitly add noise. Specifically, we add noise from a Gaussian distribution. And we can prove that this way of clipping client updates on the device and adding noise on the server satisfies differential privacy. I'm not going to go into the math details, but you can prove that this is differentially private. Now, notice one thing here. The devices have to trust that the server adds noise on their behalf. If that noise addition, which I'm showing on the server in this cloud, does not happen, then differential privacy is not satisfied. This is a crucial step. Both clipping and noise addition are important to satisfy the differential privacy that we talked about earlier. So even though this is a good approach and it leads to arguably good utility, there's still a lot to be done in order to improve utility of differential privacy in federated learning, but we can get sort of good utility for some applications. It requires that users place some trust in the server and trust that the server is going to add the noise before it releases anything to engineers or to other devices. So there's a different approach that does not rely on trusting the server. It's called local differential privacy. And here, notice what's happening. The clipping step and the noise addition step both are done on the device. This is very different from what we saw on the previous slide, because on the previous slide, we were relying on the server to add the noise explicitly to get privacy, whereas on this slide, each device itself will clip and add the noise to its data. So whatever leaves the device is already a noisy version of that update, a clipped and noisy version of that update. But the problem with this approach is that because each device will have to clip and add noise to each update, you can imagine that what the server is going to see is basically a bunch of noisy updates. And so when you aggregate noisy updates, that amount of noise is going to accumulate. And so the updated model is just going to be significantly worse. And we can prove this mathematically. There's nothing too difficult or strange about it. But intuitively, we can see it. So that's why this approach is very nice in theory. And it allows us to make strong claims about privacy and about not having to place a lot of trust in the server. But in practice, if we use it alone, it leads to a significant drop in utility. And so the algorithm that I'm going to show you in a bit really tries to address this question that I'm showing on this slide. Can we really combine the best of both worlds? I want to get the utility that I get under the central differential privacy world, where somehow I trust that the server adds noise on my behalf. But I also want to preserve the privacy guarantees that I get in the local differential privacy world, where each device adds noise to its updates. Can we find somewhat a sweet spot in the middle, where I don't have to put too much trust on the server, but at the same time I can get good utility? And that's what the algorithm that I'm going to present is going to achieve. Yes.
Yeah. Can I have one question, please?
Yeah.
You said that like this local differential privacy leads to somehow worse model, but it somehow, yeah, I would like you to like maybe present the intuition, because like from my point of view, because you add this noise, like let's say independently on each device, then like doing this like averaging, then this noise, for instance, in independent normal noise with zero mean, it will somehow cancel out on the master because of a law of large numbers, right? But if you add it just at the server, it's not gonna, you don't get that effect.
Yeah, so that's a very good point. So because we're adding independent noise, yes, it's zero mean, but the variance is going to grow, right? So if you take a bunch of Gaussian independent random variables and you add them to each other, then the sum of n of them is going to have a standard deviation that is root n times the standard deviation of each one of them. So it's never about the mean, because even the server, when the server adds noise, the server is going to add a zero mean noise. It's mostly about the standard deviation of the noise. And that's what really impacts the convergence guarantees of any optimization you're doing. And so if each device is adding noise with standard deviation sigma, then if I have n devices participating, say 1,000 of them or something, then I would have root n times sigma as the standard deviation of the final noise added after aggregation. And so that's why there's this root n factor between the local and the central models of differential privacy. And that's what ends up oftentimes hurting utility a lot, that root n factor.
Okay, so you don't do like a mean, you rather do summation. That's the problem, right? Because if you would do mean, then you would get like sigma over square root of n, right? And then like having more devices would be beneficial for you. Well,
I mean, if you're doing, it really is a matter of how you're viewing this. We can do means or summations. If you're doing a mean operation rather than a summation operation, then the sensitivity of the query itself is smaller by a factor of, say, 1 by n. So the server would have had to add a noise that is smaller by a factor of 1 by n because the sensitivity is smaller.
All right.
So really it depends on how you're viewing this. But yeah, I mean, mean or sum, these two models have a root n sort of gap between them in terms of noise or in terms of utility performance. And that's pretty well established across multiple canonical statistical tasks.
Thank you.
All right, so yeah, so this is one approach for trying to bridge the gap between the two. There are other approaches that rely on secure multi-party computation. Very interesting works. I invite you to take a look at the paper Advances in Open Problems in Federated Learning if you would like to better understand the other line of work that uses secure aggregation or shuffling, but this is just one other strategy altogether in some sense, what I'm going to present. And so the best way to present this algorithm is via an example, and it's going to hopefully be to be simple enough and quick enough. So let's assume that we have this very simple setting, 20 devices. Each device has a word. As we said, we're going to restrict our attention on one word per device. We don't have to do that in general. And let's assume here that moon, sun, they are popular because they appear 4 times. Star is also somewhat popular because it appears 3 times, but all the other words only appear once, so they're not that popular. So again, this is very much a toy example. In reality, we have millions, if not hundreds of millions of devices with many words each. So this is mostly just for illustrative purposes. And so here's how the algorithm is going to work. It's going to execute in rounds. This is how cross-device or cross-silo FL work. We have the notion of rounds. So we're going to execute in rounds. And in each round, there's going to be 3 steps or 3 phases. So in step 1 of round 1, what we are going to do is we're going to select at random 10 devices. So say I selected those 10 devices out of the 20. Again, in practice, you have a much larger fleet of devices. They're going to sample many more, not just 10. You're going to sample 100 or 1,000 or more. And so because we are in round 1, I'm going to ask the sampled clients to send just the first character of the word that they have. Just the first character of the word that they have. Round 1, first character. And so here, in the last stage of the first round, what happens is I'm going to get 3 S's, 2 M's, and for FGCL61 vote each. So you can clearly see that words that start with S or M are rather popular in this very toy example. So what the server does is that in the last stage, it thresholds these counts that it got on characters. So say we're setting a threshold of 2. Again, this is for the sake of simplicity in practice. We may want to set this to 20 or more, 16, 20, 25, to make sure that in every round, anything we're retaining appears at least 20 times or something like that. But for this toy example, I'm going to set this threshold theta to 2. So if I set the threshold to 2, then the server learns that words that start with S or M are popular. They appear frequently. And all other words that start with all other characters are not popular because they appear less than 2 times, maybe once or 0 times. And so that's it. We're never going to discover words that start with anything other than S and M. Notice how there's a state, a server state, that we've just updated it. And so now in the second round, we're going to use this server state to ask people to do a slightly different computation. So in round 2, again, those 3 steps. First, we sample devices. We're going to get now a different sample of devices. There might be some overlap. In practice, the overlap between different samplings is 0 with high probability, with overwhelmingly large probability. And so now we get this new sample of devices. Because we are in round 2, we are looking for the second character and only the second character. But now the server is going to broadcast the knowledge that it has learned, which is only words that start with S or M are popular. So any other word that starts with anything other than S and M is not popular, and it does not want the clients to share the second character of that word with the server. So notice here, for instance, LOL does not start with S or M. Great does not start with S or M. So these 2 devices that are sampled with LOL and great are going to remain silent. They're not going to send even a single character. Whereas words that start with S or M, clients with words that start with S or M are going to send the second character. So here, we're going to get something like this. 3 counts on SU, 2 counts on ST, and 2 counts on MO. And again, the final stage of round 2 is thresholding. And I'm using a threshold of 2. So in some sense, all these prefixes, SU, ST, and MO, are kept because they each got 2 or more counts. So I'm going to add them to this tree that I'm building. And we can continue to do this algorithm. We can proceed in rounds. So you can see in this toy example, if I do a 3rd round, I'll learn a bit more. If I do a 4th round, I'll learn a bit more. Notice here that even though I had wished we could have learned star, in round 4, we didn't get enough votes on STAR. We got maybe only 1 vote or 0 votes on STAR, so we stopped learning that word. So this algorithm is a randomized algorithm. We may not learn everything, and we may learn, the very frequent words. And so this is just one sample of a run of this algorithm where at the end I learned sun and moon. You can see that we've reduced drastically how much information we're sharing to the server because we're only sharing 1 character per round. I'm not sharing the full word. I'm sharing 1 character, and that character is an extension to an already popular prefix that the server has learned. And this is important because even if you have a unique word or a word that appears on very few phones, you're not going to share a character of it if the prefix to that character does not already appear on the server. And for that prefix to appear on the server, it means that all the characters in the prefix have had to have counts in the prior rounds that are above the threshold that we're using. And again, in practice, we use a threshold that is larger than 2. We use a threshold that is 16 or 20 or 24. So we make sure that in every round, at least 24 or more clients have voted on a character extension. So this is the algorithm in a nutshell. It's an interactive algorithm because we have that state that we're continuously improving on the server. And I can tell you about its privacy guarantees. It turns out that we get a bunch of very beautiful guarantees. We get differential privacy automatically, and this is the table on the right-hand side. We, in fact, get pretty strong differential privacy. We can prove that, even for epsilon equals 2 or 1, and for very small deltas, we can set the knobs and the parameters of this algorithm, the threshold and how many people I should grab to get very good utility. And we get structural k-anonymity because in every step I'm thresholding those counts. So,
sorry, Peter, we have 1 question from the audience. Taha Toghani. Please go ahead. Yeah, please go ahead.
I have a very basic question here. Is there any inherent bias in your algorithm, since we know that, for example, the frequency of words starting with different letters is not the same, and what you actually propose here is kind of biased on the first letter of the words that are important and selected by each user. So basically, it seems that there is an inherent bias in the algorithm. How we can remove this bias there?
There is no bias. So okay, I need to be careful. If you are sampling uniformly from the population, we can prove that there is no bias. What there is, though, and maybe you are alluding to it, you're calling it bias, but it's not exactly bias, is that if you miss something from the beginning, you're not going to learn it. That's it. If in the first 1 or 2 rounds you miss an important prefix, that's it. You can never revisit and relearn that something that is popular. So there's error propagation in the algorithm, and that I agree with. And that is important for privacy. And what that translates to is that you can only learn the very, very heavy prefixes or words, like the very popular words. If there's anything that is not very popular that appears on many devices, you wouldn't be able to learn it with this algorithm. And that's why this algorithm is very privacy preserving. But it's not biased. You can prove that an expectation, you can learn the heavy elements. I mean, in the sense that, yeah, statistically, what is bias? Bias is the expectation of a computation, of a randomized computation, is equal to the theoretic expectation. If I run the algorithm many times, that's essentially the same as computing some expectation under a distribution. In that sense, there is no bias. Now, there would be a bias if we are not sampling properly from the underlying distribution, but that is a bias that all federated algorithms have. We cannot always sample uniformly and perfectly from the population of devices, from the fleet of devices. And that's an open question, actually.
Thanks.
Yeah, thank you. All right, so we're a little bit over time, so I can try to wrap up. We did experiments with this algorithm, and we compared it to one of the popular heavy hitters algorithms from Apple. It's called SFP, Sequence Frequency Puzzle. You can see the performance on this plot on the left-hand side. We computed F1 scores on Sentiment 140. Sentiment 140 is a data set. It's a Twitter data set. It has something like 600,000 users, so it's a pretty large data set. In total, there's maybe around 1.6 million tweets. I forgot the exact number now. And we ran this algorithm in a federated fashion. We divided the data set into clients. The data set is already has client IDs, so we respected the structure of the data set. And we tried to discover popular words. And this is out of vocab, meaning that first we removed all the words from a massive dictionary. That dictionary has 260,000 words. Those are English words mostly, and different variations on English words. And so what we were left with are words that do not appear in this dictionary that we used. Those are, for instance, trending words or trending hashtags or events or incidents. And so we were really after those heavy, popular, out of vocab words. It's a very hard problem. And so we compared to an algorithm, and as you can see on this plot, that with the same epsilons and deltas, we get a much better performance. And these two algorithms, they offer slightly different privacy guarantees, so they're not exactly identical, but for the sake of comparison, we've done our homework in order to put them on equal footage. But you can see that you get a significant improvement from this algorithm if you use it. All right, so I think I want to stop here, and if there's any question that's left, I'm happy to take it.
Thanks a lot, Peter. I don't know if there are questions. I definitely have one, but maybe I'll Okay, maybe I can go ahead and some more questions arrive. Maybe you can get back to the privacy guarantee slide that you had a couple of minutes ago. So I'm a bit confused about these privacy guarantees, like probably because you have gone also a bit fast. So maybe you can explain a bit in more details what is the view that you assume for the server, like that does the server only observes aggregates or they observe the individual contributions? And maybe you can clarify also where the randomness comes from for DP. I can only see this subsampling aspect, which might not be enough for DP. I'm a bit confused about the setup, I guess the assumptions.
That's very good. Both are very good questions. So let's start with the first one. We are giving the guarantees with respect to the tree with all the prefixes that are discovered in the tree, but it's the tree after we threshold.
Okay,
so
yes, makes sense.
Yeah, so if there's a character extension here to a prefix that does not have votes above threshold or counts above threshold, we don't include it in the tree, because we assume that what we're going to broadcast in every round to people is the thresholded tree. And at the end of the day, what we're going to learn and pass on to engineers or teams is the thresholded tree. And so the DP guarantees, or all the privacy guarantees that I'm talking about, are with respect to the full tree and all its stages, all its levels, that is thresholded. If we are looking at the non-thresholded tree, we don't get DP guarantees. So that's important. So like if you dig into the server and if you check the tree with those extensions at some points that are not popular, that don't have counts above the threshold, that isn't, we don't have a formal proof for DP. In fact, we don't think DP holds in that for that tree.
Right.
So no,
okay.
There is some trust that you have to place. You have to assume that the server is thresholding. It's not a bulletproof algorithm, but this is way better than shipping data, for instance, shipping words, and then assuming that the user is going to take those words and compute the counts and threshold them. The fact that we've reduced from a full string of characters to only one character per user is a big significant reduction in trust and the amount of trust that we have to place in the server.
Sure.
Okay. Yeah, and by the way, this can be combined with SMPC or MPC protocols in order to reduce the trust even more. So we can do secure aggregation on top, so that the server would not even know who sent which count on which character extension. So we can combine it with secure aggregation if needed. And you can do even more using threshold cryptography. We can design a secure aggregation primitive that only allows the server to see extensions that have received counts above the threshold. So we can be very fancy and use threshold cryptography.
Right, I see. So strictly speaking, I guess these guarantees, so that they hold for the server, you would need to do these operations securely, right? So that you can guarantee that the server sees only the thresholded tree.
Yeah. So the whole effort here was to reduce the amount of trust and the surface of attack, but you still need some. If you are trying to provide a guarantee with respect to a compromised server, but if what you care about is a guarantee with respect to the clients that are participating in the training and the devices that this model is going to be deployed to, or the engineers or teams at the company, then what we have is enough. But if you want to focus on the server itself, then you would have to rely on some extra cryptography to get some guarantees. You asked another question, Aurélien, which is how am I getting DP and not adding noise, right? So it turns out that the combination of random sampling with thresholding is enough for DP. And even though this is a result that we thought we discovered first, it turns out that the idea of, even if you have a centralized database, if you sample from the database at random, You can sample IID records, or you can grab a uniform sample and then threshold things properly. You get automatically differential privacy. And so, yeah, this is something we have designed and we've analyzed for this interactive protocol very carefully. But it's an observation that actually was in the literature even before us. So it's quite known to DP experts that the combination of sampling plus thresholding gives DP without having to rely on explicit noise addition.
Right. Cool. Then thanks a lot. I guess I have just a quick follow-up question. So I also do agree with you that intuitively this is okay, an improvement for privacy because you don't really disclose full words unless many people have them and so on, which somehow you cannot, okay, the formal kind of guarantees that we are used to do not really account for that, right? So I was wondering whether you have some ideas on how we could maybe more formally quantify these gains that are maybe at this point more intuitive. It's also this fact about how many letters that you reveal. Okay.
Yeah, that's actually an excellent question, and I have myself and many other engineers at Google have been grappling with this question. Like, how do we formalize what guarantees, what privacy guarantees we're getting from this algorithm? They're not differential privacy per se, right? But there's something interesting happening because we're reducing the amount of information drastically from a full string of characters to a single character. And we're doing this interaction with all these things, including thresholding and so on. We have not succeeded to find a formal kind of definition for a privacy guarantee that we're getting from this algorithm. But one thing we have convinced ourselves is useful is very similar to how in machine learning there are these attacks that are done on the model to audit it. Like, you can train a model, it could be a generative model or a classification model, and then you can do membership inference attacks, or you can do some type of secret share attacks to see if the model has over-learned a sensitive attribute or memorized some unique training examples. We believe that in analytics, for heavy hitters and other tasks of analytics, we should have something equivalent to model auditing. Very similar to how we do attacks on models, we do secret share. We could here, for instance, also come up with interesting attacks and metrics that we can use to empirically quantify what have we memorized. If I run this algorithm many times in simulations on data sets, and I have in those data sets a secret that appears, say, on just one client or on a few clients, how often does this algorithm spit it out or memorize it, discover it, you know? So you can compute such quantities and do auditing of these analytics tasks. And we think this is very important. But we have not been able to formalize this into a privacy notion in some sense.